3.4 is velocity and other rates of change. Alright, so if I have a function that represents the height, let's say height with respect to time is 5t cubed plus 10t minus 6. Alright, so if that's the height equation, it represents the height of an object or whatever. If I wanted to find the height, the change in height, well, the change in height is the derivative of height, so the change in height would actually be dh dt, and we call that velocity. So if we want to find the derivative of a height equation, it is always going to be the velocity. If you want to find the derivative of position or distance, anything that is a linear dimension, its derivative would be velocity. So the velocity here would be 15t squared plus 10. What do you suppose the rate of change of velocity would be then? If you're changing velocity, what are you doing? My volume is at 50, so I don't know what's going on. I'd have to restart it. Alright, back to my question. If I want to find dv dt, that would be the acceleration. Okay, in this case it would be 30t. So the derivative of height is velocity, derivative of velocity is acceleration. So the second derivative of h would be the acceleration. You'll see h sometimes, I'd say more often you'll see s of t, and that's the position. Okay, if the position is 4t squared plus 6t minus 1, then the ds dt, which is the velocity with respect to time, would then be 8t plus 6. And the second derivative of position is the first derivative of velocity, which is acceleration. So it'd be 8. Okay, that's a lot. I mean, that's just like straightforward information for you. There's a lot more to this section. Let me just give you one example. This is something I made up in my notes. Trying to compare if I have time versus acceleration. Who's in physics here? Raise your hand. Okay, these two are. No virtuals are in physics. Kevin, I can never tell. I've never seen. I don't even know what you look like, Kevin. Okay. So if I ask you, what is happening right here? So if this represents a car or something, what's happening to the car right here? How would you describe it? Okay, so Cody said it's got a constant velocity. Most people will always say that, and that's what's tricky about this. Because it actually doesn't have a constant velocity. If this was a velocity function here, then it would have a constant velocity. But what we have is an acceleration that's positive. And if we have a positive acceleration, then the velocity is increasing. Because the acceleration is above the t-axis here, right here, the car is speeding up. Speeding up. Where are we right here? Is the car speeding up here? Jordan says no. Owen says yes. Cody's not sure. He thinks he has an idea, but he doesn't want to say it. Mason, what do you think? You say yes? I would agree. Car is speeding up. Why? Because the acceleration is positive. Okay, that means the rate of change of the velocity is positive. It's getting faster. Finally, we get to this point right here, the acceleration is 0. Okay, and that's cruise control. And that would mean that the velocity is constant. Okay, so if there's a positive acceleration, the object is increasing. If there's a positive, if this is the velocity graph versus time, what's happening to the object right here? Slowing down, speeding up. Owen's saying to the left, right? To the right. Maddie's saying, okay. Right here, the object is going to the left because it has a negative velocity. So in calculus or in physics, it's either going to the left because it's negative or it's going down. There's two different scenarios. Like one problem might be up and down, one might be left and right. So let's just go left and right. It's going to the left right here. Now it's going to the right. It's still going to the right because the velocity is positive. Here it changes and it starts going to the left. Here it has a positive or a constant velocity. Okay, so that's just an introduction. You need to know that the derivative position or distance is always velocity. Derivative velocity is acceleration. There's actually a name for the derivative of acceleration, and that's E prime. That would be the jerk. If something jerk, it is the third derivative of position or the first derivative. It's like a change in acceleration. So if you're accelerating, all of a sudden you really hammer it, you get jerked. That's called a jerk. And derivative of jerk, and I'm not kidding, is snap. The derivative of snap is crackle. And the derivative of crackle is, any guesses? Pop. Sounds like Rice Krispies to me. But that's what they're called. At least what I've seen. Alright, we'll see you next 2 weeks from yesterday? Wow. I'll post more video on 3.4 in the near future. I can stop recording. Thank you.